Okay, and in the previous classes, actually we have discussed about FM demodulation techniques like a frequency discriminator or balancer frequency discriminator. And the basic concept is the conversion of frequency variations into amplitude variations and from amplitude variations to recover the modulating signal. And here the same techniques is also referred as a slope detection or balancer slope detection. Earlier we are named as a frequency discrimination, and the same thing is also referred as slope detection. So here we'll discuss about another technique for FM demodulation. Actually that is not there in our syllabus, but to discuss the next topic, that is a pre-emphasis and de-emphasis. Okay, and here we'll refer the topic as a pre-emphasis and de-emphasis. This is the actual topic that we'll discuss. And to understand the concept of pre-emphasis and de-emphasis, okay, and here I will discuss about another FM demodulation technique, and here it is not a new topic. And for this demodulation technique, mostly we'll concentrate on mathematical representations instead of functionality of the circuit elements. Okay, and here the block diagram is similar to the previous case, like it is a FM wave input signal, and now we have to make this FM wave into frequency and amplitude variations. Frequency and amplitude variations. One approach is a tank circuit, and now I'm using the differentiator because slope that can be calculated with the differentiator, and with this differentiator, okay, and which is a substitution for a resonant circuit or tank circuit, which will convert frequency variations, only frequency variations, into frequency and amplitude variations. And however, we'll use the envelope detector, the same process, to recover modulating signal. So now we'll discuss about differentiator, how the differentiator makes FM wave into frequency and amplitude variations. And frequency modulated signal in time domain that can be represented by Vfm of t is equal to AC into cos of omega ct plus we have the equations like kf integral m of t dt. There are some constants like 2pi or some other, and it's the basic concept for the frequency modulated signal. Okay, and here if FM wave is applied to the differentiator, that is dVfm of t by dt. If you are taking the differentiation for this signal, now the differentiation for the signal is AC into sine the same omega ct kf into integral m of t dt multiplied by differentiation of the argument d by dt of omega ct plus kf integral m of t. So finally dVfm of t by dt is AC into differentiation of this argument is nothing but omega c plus kf m of t into sine omega ct plus kf integral m of t dt. So now you can observe for FM of t, Vfm of t, okay, and modulating signal is in terms of the cos signal. That means a frequency, only frequency variations. But if I apply the differentiator, okay, and here we have the frequency variations as it is. In addition to that, amplitude, earlier amplitude is a constant amplitude, a suffix c. Now it is varying a suffix c plus kfm of t. That means from these equations we can conclude differentiation dVfm of t by dt is proportional to m of t. That means amplitude is proportional to m of t. So dVfm of t by dt is represented in terms of the amplitude as well as m of t. M of t is represented two places. One is inside the argument and another one is at the amplitude. So now with the differentiator, it is possible to make only frequency variations into frequency and amplitude variations. Okay, and even with the practical implementations, we can use the differentiator instead of the resonant or tank circuit to make this implementation. So now, what is the need to discuss this topic, to introduce the concept of pre-emphasis and de-emphasis? Okay, and that we can discuss. Okay, and here, okay, and for a system in general, system that can be represented like this. It is x of t, y of t, and it is a transfer function h of omega. In frequency domain, x of omega, y of omega, or h of omega is equal to y of omega by x of omega general, or output y of omega is equal to h of omega into x of omega. The same relation for power spectral density that can be represented by input power spectral density is S x of omega and output power spectral density is S y of omega. Now power spectral densities are related by S y of omega is equal to h of omega magnitude square into S x of omega, which is nothing but output power spectral density is equal to input power spectral density multiplied by h of omega magnitude square. Now we'll discuss the same thing for differentiator. And that is a demodulator in FM case. Okay, and here demodulator is a differentiator, and we know the transfer function for the differentiator is j omega, and we'll discuss about the input signal is a noise signal ni of t, and output signal is n naught of t, like x of t and y of t. Input is ni of t, n naught of t, and we know that input is ni of omega, n naught of omega. Okay, and similar to the previous notation, we can easily relate these two. Now my requirement is, what is the input power spectral density, what is the output power spectral density? And here, according to the previous notation, output power spectral density S naught of omega is equal to j omega magnitude square into S ni of omega, or simply S n naught of omega is equal to omega square into S ni of omega. This is a relation for differentiator or demodulator representation. Output power spectral density is equal to omega square into S ni of omega. Okay, now Sni of omega is input power spectral density. So for example, if input noise is white noise, then Sni of omega is equal to eta by 2 or constant. Then Sn naught of omega is equal to omega square into eta by 2. The main representation for Sn naught of omega is equal to omega square by n by 2 is noise effect increases with frequency. It is a basic concept for the introduction of pre-emphasis and de-emphasis. For low frequency, there is no impact of noise, but as the frequency increases, obviously the impact of the noise increases. That means high frequencies are affected more for FM demodulation. So to overcome this problem, we'll use the concept of pre-emphasis and de-emphasis. So the basic concept for the pre-emphasis is boosting higher frequencies, because we know with the FM demodulation or FM process, higher frequencies are affected. That's why before the process implementation, we'll increase the higher frequencies, we'll strengthen the high frequencies. And if you are implemented pre-emphasis, normally it is implemented at the transmitter side. If we increase or we strengthen the higher frequencies, the counter or opposite function that we have to implement at the receiver side, and that component is called emphasis. That means we'll reduce the strength of higher frequencies, and we have to place the same thing opposite of pre-emphasis in the receiver. So here the reason for introducing pre-emphasis and de-emphasis is effect of the noise is high for higher frequencies, and it is applicable only for the AM frequency modulation, and there is no topic of pre-emphasis and de-emphasis in AM, because noise is not affected. AM demodulator or noise affected with reference to the frequency. Okay, now according to this representation, the transfer curve for the pre-emphasis is there is no modification for the low frequencies, just we have to strengthen high frequencies. Now the transfer curve for the pre-emphasis is lower frequencies are maintained the same and higher frequencies are increased. It is a frequency and it is the amplitude. And the corresponding representation for the de-emphasis is we have to maintain up to lower frequencies as it is, and we have to decrease the same thing. It is the amplitude. It is a basic requirement according to this representation. Why we are affecting the higher frequencies? Because noise effect is high for higher frequencies. That's why we are intentionally we are increasing higher frequencies before the actual process is going on. And if noise is affected, and we are already increasing the higher frequencies, and that can be normalized as far the representations are concerned. And to implement the same thing, de-emphasis is more or less like a low pass filter. So that's why the circuit diagrams for the pre-emphasis and de-emphasis, or pre-emphasis circuit diagram, that can be represented by the components like this. Okay, and obviously you can hear lower frequencies are maintained and higher frequencies strength is improved. With the de-emphasis representation, as I mentioned, it is more or less like a low pass filter, and the representation may be like this. So here, according to the representation, pre-emphasis is placed in the transmitter, and obviously the very first component in the transmitter side is a pre-emphasis, because we have to work these modifications on the modulating signal itself. And similarly, de-emphasis is the last component in the receiver. Okay, while recovering the modulating signal, we have to counter operate the operation performed at the transmitter, which is nothing but de-emphasis. So in the FM transmitter and receiver circuit diagram, okay, we can identify the positions of this pre-emphasis and de-emphasis, and these circuits of these concepts are particularly meant for only frequency modulation, because we are using the differentiator or the slope detection for FM. So these are the concepts for the pre-emphasis and de-emphasis.